Hey guys, how guys? So my name is Nelly. A blockchain dev, and I recently participated in a CTF. Who knows what a CTF is? Or you've had one. Okay, so a CTF, I think it's a competition where I don't know how to say it actually, but it's a competition where there are challenges and your goal is to just get a flag. So it's like an answer to some challenge. So that's the goal. And then you have teams competing in the CTF. So I participated in one. Actually, this is my second time doing the Perfect CTF. Honestly, I do them just for fun because they have Web3 challenges, and I think most of us just relate to Web3 mostly. So I only do them because they have Web3 and cryptography challenges, and yeah, just for fun. And so I did the Perfect Root CTF, and I wrote this very detailed write-up. As you can see, it's a 45-minute read. That's a long time, right? Yeah, yes, it's a 45-minute read, and it's very shocking, but I think my goal was not just to, show you guys how I solved the solution or just show you that I did this and I got the flag or got the answer. I think that the goal is to just make you guys, as the readers, to even also discover the answers on yourselves, to have mental models while you're reading my write-up. Yeah, so just to make the reader even understand more about the write-up, not just giving them solutions and telling them, yeah, this is just what I did and I did this and that and that. So that's why I wrote such a detailed write-up. And before we even start, so who writes technical content here or has a blog that they write content? No one has a blog. Oh my God, you guys, you're not serious. But okay, you've tried writing one. Anwar, you don't have a blog. You used to. That's sad. So sometimes when we write technical content, we just want to write Maliza and Evil. You don't really care about who's reading that. You just, yeah, see, I just wrote it, it's gonna be there, and that's it. So if you want to be a good technical writer, or at least you're doing it for, for a genuinely purposeful meaning, I think you should have some rules where you understand your reader, who's reading, how are they gonna feeling when they're reading my write-up or my blog or my technical content. So there's some laws where you're writing technical content. So the first one is, oh, okay. I think I'm not sharing this window. Let me just. Yeah. So these are like the 5 laws for writing any technical content. So the first one is the first one is context before content. Before you show the reader any code for whatever solution you're giving them or for whatever reason you're writing your technical content, just show them the context first. Just tell them, okay, so what's the context behind this code? Because if I show you, like, let's say a random piece of code, yes, maybe you can read some code, but you don't have all the context. But if I write the context before I show you the block of code, I think it's gonna be even easier for you to understand the code. That's right, right? Yeah. And the second law is failures are features. So when you're also writing, like for example, when I was doing the CTF, there's so many failures. Of course, you're not gonna get a flag on the first try. So as for me, I try to document the failures. When you're I thought I got a flag, this is what I did, but I got a wrong answer. You show all of that so that the reader just follows you through, follows your journey, and they're like, oh, okay, they have that mental model of what you did and even what you might do next. So it just builds up their knowledge as they go on reading the article. So just show all of your failures. Another thing is respect reader intelligence. So when you're writing, don't assume reader's intelligence. Don't assume that I'm writing this for a very intelligent person or I'm writing this for a beginner. Try to just balance the context. And I think one of the things that I did in this sorry, one thing that I did in this article, I think I kind of oversimplified it a lot, which is not a bad thing, but for someone who's very technical, let's say a protocol engineer, this is not a good article for them because it's oversimplified. Of course, they know all of that, right? So when you're trying to write technical content, just try to see if you're serving different audiences at the same time. Don't write it for protocol engineer, don't write it for beginner. Make sure that you're just balancing your content. Yeah, so maybe you could start by explaining very thoroughly or writing, a sentence for a protocol engineer, and then for a layer 2, for an intermediate person, then explain. And then for a beginner, you can now go even more further explaining the concept. And then another one is architecture is greater than code. So again, most writers, they show the code first, but, explain the context. What's the context of this code that I'm showing the reader? And so just flip the order, show the context, and then show the code. Yeah. Another thing is make the invisible visible. So as you can see, the things that confused you are the things that you should explain most. So the things that confused me when I was trying to solve these challenges are the things that most would confuse the reader as well, right? And if it confused me, they could be like, oh, okay, so if it's not done like that, then how else is it done? And then they have now a mental model of another solution for the same challenge, right? So this is just some of the simple laws when you're writing technical content. And yeah, let's go to the star of the show. So how many of us are like Solidity devs? Nice. So I personally, I'm not very good at Solidity. So even this was a learning experience, but I'm just gonna try to explain, what I learned and everything. Okay. Let me just add this window. Perfect. So let me just take you guys to the exact, this is the page, this is where the challenges happen, or where I was doing the challenges. As you can see, there's web. Okay. There's welcome, there's survey, there's malware category, there's DFIR, which I don't even know what it means because I actually am not good at this. I think this is reverse engineering, there's IoT, there's cloud, there's OSINT. OSINT is general intelligence. So it's just something that anyone can do. It's how good are you at finding out information, at looking through the internet and everything. So I think OSINT it's pretty much for everyone. And then we have mobile for the mobile devs. We have now Web3. As you can see, I did all the Web3 challenges. And then we have PWN, I think this is Spawn. And then there's AI, there's web, there's miscellaneous, there's cryptography, of which I did one in the cryptography, and then there's boot to root. So yeah, so if you're not even out, okay, I think it's more for the Web2 people, but as you can see, it has Web3 challenges, so it makes it easier for you as a Web3 dev to even participate. Okay, so I did 1, 2, 3, 4. I did 4 of these. In the write-up, I explained this, and this. I didn't explain this. It's actually very simple. And then I also did one for cryptography, and yeah, that's it. And one for MISC. I think, yeah. So this was the first one. So this was the challenge description. So the vault holds its secret deep within the bytecode. So when you hear bytecode, who has an idea of what bytecode is? You guys raised hands and said you're Solidity devs. So who has an idea of what bytecode is? Or maybe you've heard of it. You've heard of bytecode, right? Okay. Yeah. So I'm going to explain what bytecode is, but yeah. And then this was just the challenge description. And then you're told that find the exact and message value that makes the vault open. And then you're given a contract address, and then the network, and then the flag format. So from that, as a Solidity dev, I think you should just have a rough idea of what you should be doing, right? Okay, so the first thing is, of course, you have to go to the contract address on Sepolia. Of course, I think I was looking through it. Yeah, this is the contract address. And the challenge says that the vote holds its secret deep within the bytecode. No source, no comments, just called silent opcodes. Okay, who has an idea of what opcodes are? Or you've heard of opcodes? No one. Okay. So basically what you had to do is just so this is what you see when you come to the address given. As you can see, this is the first thing you're gonna see. This is the transactions for that address. There are two transactions. One failed, one is successful. So what next would you do? I think the next thing is to click any of this, right? So just click this, see its details, and you can see the status. It failed with a send 32 byte call data. Does anyone know what call data is or has an idea? No. But yeah, it failed with failed with error, send 32 byte call data. And then there was another transaction which was successful. This one was successful, and when you click to show more, there's nothing. It just calls a basic function, which is I think a fallback function. Yeah. And then so let me just take you guys through how I solved it. Okay, so this is just, introduction on, how to write good technical content. You just want the reader to invent the solution. You're not showing them the solution, but you're just taking them through the journey where they can even discover the solution and invent it on themselves. So this is the first challenge. So for those who don't know what a contract address is, I think this is a pretty simple explanation of what a contract address is. Yeah, it just tells you where a smart contract lives. A smart contract was deployed, so where does it live on the Ethereum blockchain? So the first move is to obviously analyze or go to Etherscan. And as you can see, I looked at both of the transactions. This is the first one that failed with a send32 byte call data, and then this other one was a success. So when you see that a contract has failed with a send32 byte call data, that means that some of the data being passed, or some of the parameters, they are 32 bytes. Okay, so for storage, for Ethereum, it's persistent storage, and every slot, so it's stored in slots, has to have exactly 32 bytes. So it can be more than that, but it can be less, but no, not more than 32, yeah? So what happens is, let's say you declare variables like you into 56, maybe A, or into 56B. So the first one is gonna be given a slot 0, the second one is gonna be given a slot 1, just like that. That's sequential, but there's two types of storages. That's sequential. So you're giving them as they come, 0, 1, 2, 3. But there's computed, where you actually compute the storage, which is you obfuscate the whole data storage, and that makes it very hard for someone to find the data. And for this challenge, that's what that person used. They used the computed storage slots. Okay, so I thought that the contract, it wanted exactly that 2 bytes of call data. And since the failed transaction sent 0.05 ETH with empty call data, I just thought that I need to just send a transaction with 32 bytes of something, maybe with the correct value of ETH. Yeah. Oh, by the way, who has read this article? If you've read it from start to finish. Ouch. I'm disappointed. Uh-huh. Why didn't you just read the whole of it? Why did you? Was it too long for you? Mm-hmm. Uh-huh. You said you read the article? How was it? How was it?
Nice, very informative, I would say,
Mm-hmm.
and in depth. There were how many challenges? 5 challenges.
Yeah.
Actually, it was interesting to see that how to solve this different.
Yeah. So I earlier mentioned about bytecode. So the EVM does not understand your code. It has to be converted to something else that the Ethereum virtual machine can have an idea of. So it needs bytecode, which is just a series of hexadecimal numbers that represent low-level instructions, which are called opcodes that the EVM can execute. So I think this is a challenge for everyone. You need to understand the EVM at a fundamental level. So maybe bytecode, opcodes, and everything. I think it's very essential. As much as you think that we're not using this anywhere or I may not need it, I think it's essential to. Sorry, I think it's essential to just know that low-level stuff. Yeah. Okay, so this is the bytecode, which is machine code that can be computer readable. Of course, they're just individual assembly instructions. Now, this is like the CPU instructions for the EVM, like the very good instructions that the EVM can understand and even execute. So when you go to this contract, to find the bytecode, this was the first transaction. When you go to this contract, as you can see, the source code for the contract is not verified. Because if it was verified, it would have been ingekuwa tunaona hapa hivi. So this is just the bytecode. And if you read the article, there's a difference between constructor bytecode and runtime bytecode. So this is runtime bytecode. So what's constructor bytecode? Let me show you. So this is the contract address, right? But we need to look at the transactions that created that contract. You see, there's a difference, right? So nakuja tu hapa kwa the creator address, and then you're gonna see all the transactions they've made, right? So as you can see, there's a contract creation transaction, and it creates the contract that we're looking at. So what you have to do is just so this is the contract creation transaction. Just click that. So it just takes us to the same one. Also, I think what you should look at is this transaction hash, which was the creation for that. And then what you're gonna get is now, this is the constructor bytecode now. So constructor bytecode has the constructor code, it has the constructor parameters, and then it has the runtime code. So if you want to investigate the constructor code, this is where you go at the contract creation transaction, and then you get this bytecode over here. So that's it. Yeah, but this one, of course, like I said, the other one that we saw is not verified, so you would not even get much of it, from it. Yeah, so this is the one that you initially look at, and then the next step when you look at that. Okay. I need to hide this. Yeah. Okay, so like I said, there's contract creation code and there's the deployed bytecode. So for the constructor bytecode, which is the creation code, is the one it runs once when the contract is deployed. So when you deploy your contract, it just initializes everything. So initializes the logic, the storage values that are supposed to be there, that's where they're stored. And then we have the runtime bytecode, which is now the one that we saw, which is this one. The runtime bytecode runs every time someone interacts with the contract, and it handles all the function calls, and this is exactly what we're looking at. So for you to even get something off of the bytecode, you could look at it from two views. So you could switch to opcodes view. which I say is just the low-level instructions that the EVM can understand. So you can look at the opcodes and see what happened, but you could also decompile the bytecode to see if you can get anything important from it. So when I try decompiling the bytecode, let me see. So you're gonna get this fallback function. But I also discovered another bytecode decompiler. I think I was working with it yesterday. That itanipea like a very detailed code from instead of a fallback function. I think it's EVM. Let me just decompiler. Yeah, of course, website. It's this one. And this one has a decompiler that it works very, very well. I don't know where I found it. Oh, yeah, just come here, decompile. You just put the contract address. In this case, I think our contract address is, let's just copy it. I want you guys to just see the difference between the Solidity decompiler, the one that's here, and this one. So this is our contract address. We're using it on Sepolia. I'm just gonna copy this bytecode and then decompile it with this one. And also, yeah, and you also have to remove the OX prefix for it to give you a better result. So let's decompile. As you can see, this one gives me such a detailed code, right? When you compare it with this one, it's pretty much detailed, and I wish I had it at that time when I was doing the CTF, because it would have already helped. Because straight from when you look at the code, you can see there's something being stored over here, which is 32 bytes. Okay, so for the opcodes, when it's 0x20, that means that there are 32 bytes being pushed. Yeah. As you can see, I can already see that there's a hidden value over here. I can also see another one being stored. So I think this would have been very easy if I had discovered this decompiler instead of this one. But either way, let's proceed. So you can switch to opcodes view, and then this is what opcodes are. They're just the individual instructions that the EVM executes, and each opcode is represented by 1 byte, that is 2 hex characters. So 0x20, those are 2 hex characters that represents an opcode. As you can see, 60 just means that you push 1 byte onto the stack. Oh, and another thing that I failed to mention is that the EVM uses stack instead of registers. So it doesn't use like the x86 architecture, uses the stack. And then when we have this hex character, that means that you just duplicate the stop stack item and everything. So again, I want to challenge you guys, go read about opcodes. Just learn the EVM fundamentally. I think this would be easier if I actually had. And then now when you decompile the bytecode, you get this fallback function, which is, this is what gets called when you send a transaction to the contract. And the Solidity decompiler is not perfect, as I compared it to the other decompiler over here, which works way better. And then, yes, so I think the only option is to look at the opcodes and make something out of the opcodes. So I talked about the call data. I'm going to talk about that later as well. So when you see an output of push 1 OX20, that means that you push 32 bytes onto the stack. So 0x20 is hexadecimal. When you convert it to decimal, it's 32. So that's 32 bytes. And then call data size just means that what's the size of the input data that was sent to the transaction. And then EQ just means that check are they equal. And then the other thing is if they're equal, just jump to the other position, which maybe it's another line of code. So in this case, just jump to this OX4C. And then if they're not equal, just revert the transaction. Yeah. So that means that it was checking, did you send exactly 32 bytes of input data? If yes, just proceed. If no, revert with this error. So that means that the transaction that failed over here, Yeah, this transaction, that means that it did not have that 2 bytes of call data because it did fail with this exact error. Yeah. And then, yeah, so call data is just the input data that you send when you call a contract and everything. So I think this challenge was really just testing. Do you know how to read opcodes? So do you understand Ethereum storage? If you did, then that's very easier for you. Because all of this is just dealing with the storage and the stack and everything. So store it to memory and then hash it and then call value, get the message dot value and the amount of ETH, and then load that from storage, compare, and then make a decision. I think it's very, very simple, very, very straightforward. Yeah. I think I talked about a storage slot. It has to be 32 bytes, not more than that. But there's a way you even compact them. Let's say you have a variable A, and then let's say it's not even, let's say it's 15 bytes. So Solidity compacts them. So let's say it's 16 bytes. So if we have another variable, if it's also 16, it's going to compact them together. Instead of just leaving the other slot, the 16 other bytes empty, it's going to compact them together. Yeah. So I think the first thing that I did, if you know, or if you've used Foundry, there's a way you could use a Foundry cast method to call or get the data from transactions. So what I did, I tried to when you look at the opcodes, you can see that there's a slot defined over here. Like this is a slot. When you push 30 bytes onto this slot, so that's what the opcode says. So what you can do, you can query that slot. So you just use past storage. Yeah, this one over here. Where is it? Yeah, you could just use cast storage and then it just gives you what was stored at that time. Exactly this one. So cast storage and then the contract address, the slot that you want to query, and then you can use a public RPC URL or any RPC URL as long as it works for you. Yeah. So as you can see, when I queried what was stored at that exact slot, I got a 0. So I thought, okay, if it returns a 0, then I think this should be the flag. And then when I put that as a flag, it was incorrect. So I had to just now rethink the whole thing. Okay, so the storage was 0. Sorry, 0. So what happened? So when you come to the contract over here, like I said, you have to look at the contract, the deployer wallet address, which is what I did. And then you can see, you could look at this is the contract creation transaction, and then this is the transaction hash. So we could get a lot from the transaction hash because it was, what was being passed when this guy was deploying the contract. Yeah. And when you do that, when you click to show more, you get something, you get a constructor value. This one over here. Yeah, and then when you decode it, let me just view it at UTF-8. I think as much as they're just random characters, you can make something out of it. There's something I can see. This one, analyzing bytecode like a pro. I think that is lit speak. So that means that we are actually somewhere. And I actually thought this was the flag as well, because even most of the flags in CTFs, they're written in lit speak. So I also took this as a flag, but of course it didn't work. So I had to also just rethink this whole thing through. Yeah. As you can see, I scroll past that and I click the transaction, the creation transaction, and then I saw the constructor bytecode as well. And then when as the constructor parameter, when you decode that constructor, you're gonna get this. Oh, I think we skipped something. So we're gonna get the analyzing bytecode like a pro, and then when you now look at the constructor code. This constructor code. As you can see at the very end, we have some interesting values. Yeah, and of course, when you look at the constructor code, I mean, of course, I don't know how, I just didn't look at the constructor code and I thought, oh yeah, this is interesting. Of course, you have to try to convert it from hex to decimal and maybe even ask AI to help you out. So I think good thing with AI right now, it can write from the bat or just on the bat, decode it for you. So it saves you a lot of time. Yeah. So when you decode that interesting value at the end of the constructor, you get I got this value as well. So I thought, okay, this doesn't seem like a flag because I'm used to flags being written in lit speak. So, but either way, I tried the flag and it was correct. So the problem or the trick was that, remember I said that there's runtime bytecode and there's constructor bytecode. So what was stored so the runtime bytecode was pushing 30 bytes of something, yeah. But remember we want 32 bytes. So when you query the runtime storage slot, it's gonna return a 0. So what you had to query is the constructor this constructor slot, which had exactly 32 bytes. So that was the trick. And even in the challenge, the author said that the secret lies deep within the bytecode. But in this case, it's not in the runtime bytecode, it's in the constructor bytecode. So I think that was also a misdirection. So as you can see, the reading of opcodes was very, important here, because when you see push 30 and push 32, you should be able to just tell the difference. So this one is pushing 30 bytes, this one is pushing 32 bytes. And then yeah, so that was the trick actually, and I think it's well engineered. Yeah, and also since they used computed storage slots, it was very hard for you to even just find the data right off the bat. Yeah, so they were just completely different storage slots, and that means that they store different things and their hashes are different. And remember with hashing, it takes arbitrary input and then converts it into a fixed output. So if the inputs are very different, of course, it's going to give you a very different output. So if for the slot A, it had that 30 bytes, that means that the hash for slot A was different from the slot of hash B. Yes, so I think that was fundamental. So I think just storage on Ethereum, how it works, computed slots on Ethereum, that was some of the tricks that one needed to know, at least to be able to solve this. Yeah, I think that's it for challenge 1. I don't know if anyone has a question. Okay, so I think I don't want to keep explaining the challenges in that detail. I mean, the article is here and it does that. So I'm just going to touch on just the fundamental things that the challenges were testing. So for the second one, this was the description. Equals in the cab. Equals. So this was the description, and then you're given 2 contracts, and then you have to look at the contracts and get something out of it. So when you hear about 2 signatures, 1 hand, that means that there were 2 signatures, but they were signed by 1 private key. So this just takes us to the fundamental ECDSA. So who has heard of ECDSA? Okay, so I think I even had a Wikipedia tab open because I think that's the most important thing. So elliptic curve digital signature algorithm. So I think most even of the Web2 websites, most of the cryptography on the web is based on ECDSA. And side note is that people are worried that quantum computers are gonna break, the current infrastructure we have, given that ECDSA is gonna be broken by quantum computers. The reason is because we have the district log problem. If you don't know about it, it's when you're given, let's say, a public key, and you're given a private key, and you're also given a generator point, which is like a starting point on the curve. If you're given even the public key and the generator point, it's very hard for you to compute the private key. So the whole security for ECDSA on the elliptic curves is based on the district log math problem. So so the Shor algorithm I think it has already solved or it can solve the ECDLP. So that means that ECDSA is at risk here because its whole security is gonna be broken. So that was a side note. So basically, this challenge was just testing. Do you know how ECDSA works? So we have signatures, we have nonsense, we have a public key, a private key. So it was just testing. Do you understand how they work and how having one nonce or using a nonce? I think we know what a nonce is, right? Who knows? Yes.
So, like now,
Mm-hmm.
we track the number of transactions
Mm-hmm.
for which have happened now.
Mm-hmm.
Yeah.
Yeah, so actually what it means is just a random number that is used only once. So you cannot reuse it. And I think in this case, the the so some roots are never meant to be shared. So that means that he's referring to the nonces. They are never meant to be shared. You cannot reuse. If you reuse a nonce, that's a big problem. So what I was just testing is, do you know how ECDSA works, how to compute a signature? So if you have two signatures that are using the same nonce, I think you could be able to derive. So, okay, so in a signature, there are two unknowns. There's the private key and there's the nonce that was actually used. But if I reuse a nonce, I could subtract the two equations and get the actual value of the nonce, right? And then I could go into the initial equation and then just substitute the value of the nonce. And that means that since the private key was also unknown, but I know the other value, I can now get the private key, right? That makes sense.
Yeah.
Does it make sense? Okay, let me show you guys. Yeah, so this is just me trying to get anything out of the contract. These are the constructors. I walked you guys through what constructors are and everything. And then I just noticed something about the contracts and the arguments. So if something has the OXF8 prefix, if you ever see a transaction with the 0xF8 prefix, that means that it's using RLP for transaction. And when I compare the contracts, both of them were using that they were using the encoding, the RLP encoding. So that means that there are two contracts, there are two transactions, there are two signatures. One hand means that they were signed with the same private key. Yeah. And so I had to just I was, I think it was very obvious now what was the attack vector over here. And then when I looked at both contracts, I discovered that so actually for both of these contracts, the contracts were verified. So when you look at both source codes, they were the same. So that means that they had a get all function. Okay, so I think another thing that the challenge creator did, they stored the constructor values in chunks. So they didn't give us the constructor values all at once. He stored it in chunks. So it's very hard for you to make anything of something that's not complete, right? So the importance of the get all function. So when you call the get all function, you can retrieve the full concatenated data, whether it's hidden or it's in chunks or whatever, you get the full data. Okay, so I use the cast tool for Foundry, and this was the first contract. I called the get all function, and I got a lot of data. So I got so that it starts with this prefix, which is another RLP encoded transaction. That was the same for the other transaction. So okay, so what is RLP? RLP is just recursive length prefix. It's just the Ethereum's way of encoding data. Think of it like JSON, but for blockchain. Okay, so for JSON, it's human readable, right? But for the blockchain, for it to be even able to recognize that, they use this encoding protocol. Yes, so encoding transactions, encoding blocks, encoding the account states and everything. So I think the important thing is when you notice that they are using the RLP, then when you decode the transactions, you should be able now to see the values of, what is composing as transactions. If they're the same, then that means that there are two values that should match. Okay, so in the legacy transaction format in Ethereum, that was like before it was Kitambo. It was Kitambo sana. They used to have a nonce, the gas price, the gas limit, the value, the data, and now the signature, because you're obviously proving that if you're making a transaction with this wallet address, you're proving that you actually own that wallet address, and that's by you making a signature with your private key. Right. So R is just the first part of the signature. S is the second part of the signature. And then V is just the recovery ID, helps recover the public key from the signature. So when you decode, so I also wrote a transaction to just decode the first transaction. So just this is just a simple script. Of course, I didn't write the whole script. You just have to describe, what do you want the script to do? Like what exact values do you want them to be extracted from this transaction? And then that's it. So as you can see, I wanted the transaction to be extracted, the nonce, the gas price, the limit, these values, yeah, and the whole signature. Yeah, and then as you can see, I got some signature components, which is V is 27, the R, which is the first part, and the second part, I got them. So yeah, and then I did the same for the second transaction, and I got the same values, the VRS. But when you look at the transaction one, there are two values that are the same here. So the R value, which is the first part of the signature, is the same. Yeah. And if that means that they're the same, that means that one nonce was reused. They used the same nonce for the two transactions. Yeah, and that's a very big mistake that they did, because in mathematics you could always extract the. Okay, so like I said before, when you have a signature, there are two unknowns. There's the private key, which is unknown, and the nonce. But when I look at two signature and see that the nonce was reused, I can just do the mathematics and subtract the first transaction from the second, and then get the nonce value, substitute it in the first transaction, and then I can get the private key, right? Does that make sense?
Yes.
It makes sense, right? Yeah. So let me show you the math. Okay, so this is the signature. So it has the message, the private key, and then this is the nonce, and this is the R value, which is the first part of the signature. And then this is the S2, and then it's just the signature, right? But if the R values are the same, then I could always do some mathematics to subtract. I solve for the K value, and then K is the nonce, right? And then now I can now substitute the K into the first, I can now substitute K over here, right? And then what that means that I'll get the private key, because I already have the R, now I have the K, I could already now do the mathematics and get the private key. And remember, this is a private key. Yeah. Okay. I wish we could do some math on the notebook, but I think it's not possible. And then now, this is just the, plainly, different S values, they have the same R value. So that means that we can reverse engineer and get the nonce. And then once we know the nonce, now we can calculate the private key. And if you ever heard about the Sony PS3 hack attack, so that's what they did. So when they were, authenticating the game, they use the same nonce. So that means that attackers could do the math, calculate the nonce value, and get the private key. So that means that they could create any video game, and even make it seem like I actually created this video game instead of Sony. So that was one of the biggest hacks in history in nonce reuse, where you use the same nonce for very many transactions. Yeah. So as you can see, what the attackers could do, they could, now sign any code as if it was Sony, and then they could use the homebrew software that could run on PS3. We could have pirated games that could be installed, and then just the entire security model was at risk. So of course they had to update, the signing thing, and now maybe use different nonces. And I think another very critical thing is when you're also generating these nonces, because they're random numbers, please make sure that you're using a very good cryptographically secure random number generator. Because if you use a faulty one, then it could also leak some things about the nonce generation, and then it's also a security issue. Like for example, I think in 2013, there was a hack on Bitcoin Android wallets. So the guys, they used the Java util random number generator. That one is not cryptographically secure. So what you could do about that is just it leaked something about the private key. So they could obviously do something and even steal money for a lot of people because it's Bitcoin, yeah. So that's the whole risk. Do not reuse a nonce. Okay. So has that made sense? Yeah, so yeah. Yeah.
Okay. So analysis errors will not predict like maybe it's 1, 2, 3, 4, 5, 6. Or it's different.
No, it's not predictable. It's a random number. That's why it can only be used once. It cannot be predictable. It cannot be 1, 2, 3, 4, 5, 6, 7, 8. It has to be a random number that, a random number like maybe has even 32 hex characters. And even you making even like redoing the nonce or regenerating it will be very hard for you, in math, like computationally. You cannot regenerate a nonce. So it has to be a random number. Yeah. And when you're generating it, make sure that it's cryptographically secure as well. Yeah. Is there another question? Okay. Another thing that I had a problem with, so when I was calling or just getting the information about the transactions, there's this values, there's the V value, which is, in this case, it's showing 27, and then the other one was, where did it go? Oh, I kind of scrolled. So there you can see there's values 27 for both of them. So actually that was a very critical information because that means that there was an error where it was 27 and then after, okay, so the problem with the pre-IP 1555 is that the transaction now it was not secure in such a way that it was not showing where this transaction is valid. So that means that you could make a transaction and then it could be valid on both Ethereum mainnet and Ethereum Sepolia. So you could replay those transactions. Of course, that's a very critical thing. So when there's V27, it shows you where or in which era the transactions are. So if they are 27, that means that it's pre-IP. If it's 27, 28, 29 forward, that means that it's after. So it's now EIP 155. Yeah. Okay, so for the pre-IP, for the legacy ones, they had either 27 or 28, and then for the ones that includes the chain ID, so that means that for the chain ID, we will know that this transaction is valid on Sepolia or it's valid on mainnet. But for the pre-IP, you could replay both of them to see that they were actually, if a transaction is on Sepolia, then that means you could replay and it could seem that it was on both mainnet and Sepolia. Yeah. So that was just the very important thing that this one was testing. So do you know the math behind ECDSA and the risk of reusing a nonce? So when you see that the R value is the same, then that means that a nonce has been reused and therefore you can recompute and get the private key. So yeah, so basically I just had to recompute the private key. Of course, I cannot do it manually, just write a script with all the information and then it just gives you what the private key is, recomputes the private key and now derives an address from that private key. And actually this was the flag. Yeah. The private key at the bottom. That was very interesting. Yeah.
Use like packages.
Yeah, you could. Yeah, you use packages, but make sure that you use the ones that are cryptographically secure. Yeah, because some could leak something about the nonce, and attackers are always attackers. They'll find a way to get that information somewhere. Yeah.
There's something as well. They have a room where nonsense are generated using like lamps and like it shows different colors. And like they have like 60 lamps and then they generate color have code from that. And then they use that as their nonce. The web.
That's very random. Yeah. It has to be like true, it has to be true randomness. Yeah. Yeah. Is there a limit to the size of the nonce? I think basically a nonce has a limit. I think, is it 32 or 64 hex characters? I'm not sure, but a nonce has a limit, but I don't think they're all of them. Maybe it just depends with for what purpose are you, creating this nonce. So some maybe have 64 hex characters or 32 or anything. But yeah, I'm not actually sure if maybe all nonces are fixed. Maybe I'd have to think about that or just research about that. So yeah, that was what that challenge was testing. Okay, so the other challenge was another interesting challenge. It was ghost in the block. So find what the Merkle root of block that would be if the transaction was removed from it. So when I saw this, I thought immediately it was Ethereum because I was working with Ethereum transactions. So I went to Etherscan, searched for the block 90, 590, 5090, and it was I didn't see any important information. And so I tried even using Foundry's cast to even query this specific transaction, but was not given any answer or any return. So then I asked or just searched, I searched this block online just on Google, and all of my search results were Bitcoin. So I knew, oh, this is Bitcoin. And then I also saw that the latest blocks, the Bitcoin size iko 900,000. So that means that if this was Ethereum, then ingekuwa uko early 2016, because right now we are 23 million, right? So 900,000 block would be uko kitambo sana. So this was definitely Bitcoin. And another thing that even sold it is the Merkle root. It's very easy. So for just a basic Merkle root, so what we do, we have transactions, and then we have leaves. Leaves are transactions, and then we have branches. So what you do to get a branch is you take two transactions, you hash them together. That's a branch. Then you keep redoing that up until you get one hash, which is the root. So that's a Merkle root. So that means that if you want a specific transaction in the whole tree, that means that you just need three things. You probably need the neighbor or the sibling, and then you need probably a sibling, the transaction itself, a sibling, and an uncle. An uncle is just like an adjacent transaction upper in the branch. Yeah, so you just need three transactions. That means that it's just three hashes. But for Ethereum, it's very hard with the RLP encoding. It just means that you would have to do a lot to even just get one transaction from the whole tree. So another thing that made it easier is because Bitcoin just uses the binary Merkle tree, and it's very, very simple to just work with it. So I wrote a script for that. So as you can see, Ethereum uses the Patricia tree, and then Bitcoin uses the binary Merkle tree. Yeah. And then another thing that was also being tested in this challenge is that when Satoshi was creating Bitcoin, I think he was heavily influenced with the registers architecture, the x86 architecture. So how he used to do it is, so there's endianness. It's just the way bytes are displayed. We have big endian and little endian. So for big endian, it's just human readable. So when you go to the block explorer, that's what you see. That's big endian. But for you to do even operations with it, you have to reverse it. Like, for example, let's say you have 1, 2, 3, 4, 5, 6, 7, 8, right? In big endian, if you just, we normally just couple the bytes together. So it could be OX12, OX34, OX56, OX78. That's big endian. But for Bitcoin, you have to flip that order. So you start with 78. So it's OX78, OX65, OX, yeah, you guys get. So that means that when I even get something, when I remove this transaction, the value I'm gonna get, I have to flip it to little endian, and then I'll flip it back to big endian for me to even be able to make something out of it. Does that make sense? Yeah, so like that was also another thing that was being tested in this challenge. Do you know about the NDNS? Yeah, Bitcoin. Yeah. So I just use I used the Blockstream API to just get that transaction, and then I just performed all these operations. And then there's a place where I have to convert it to little endian when I'm doing this, and then convert it back to big endian for be able to get, or even for it to be very right. So yeah, this was you can look at the script. Again, you can always read this and look at the script and how it works. Another challenge was I think that was pretty much easy. It was just testing. Do you know how Bitcoin works? Do you know how to revise a Merkle tree? And then do you know about NDNS? So you have to flip them back from big endian to little endian and then to big endian as well. That is fine. Yeah, and then we had another one which was very interesting. So for this one, let me just okay, it was the smart bid, and you had to go get an instance, a blockchain instance for yourself. Let me just show you. Yeah. So what happens here is that so they also gave me a challenge, some code over here that I had to download. So when you see a 400-point challenge in a CTF, I think that shows that, you have to do a lot of work to get the points, like 400 points. I think this was actually the highest. Oh, there's another one with 500, but 400 is high. So that means that, you're not going to get the flag very easily. Okay. So what you have to do is just you solve this in browser. It's like a token to opening the blockchain instance. So you solve in browser. It actually took some time. But actually another way you could actually do this is it's a long way using Remix, but you could always solve in browser. I mean, it's just right there. Do not complicate stuff for yourself. Yeah. So the solution is found. I submit the solution, and then I think now I can launch my own instance and get these credentials. So these are the credentials to get my own blockchain instance running in my machine locally. So what I did, so when I looked at the code, let me show you guys the code. This is the code. So when I open the code, and just so that the only thing that you have to do is just call this function, this solve child function. That was the only thing. So I thought that maybe this is maybe the first layer of the solving. So you solve this, you get something, and then I'll go to now the hard thing. But actually, it was just as easy as this. You just have to call this function, and then when you call it successfully, they give you a flag. So what you have to do is just come here and then look at the flag. As you can see, I've not solved it, so I won't get the flag. So what I did now is now just wrote a script to just extract the whole thing. So you just give it all this. Of course, I used Web3 Pi. To interact with it. So when I get all these the credentials, I just I plug them into my script, and then yeah, I run it. So let's actually run it right now and see if we're gonna get a flag. So of course my script had other values, and so it looks at the current instance that's running. So this is the RPC URL. I think my script should be yeah. No, that's not it. I'm not even sure which one it was. Spore. Yes, the card. Spore. I wish I named them a bit. Oh, yeah, it's the solve bid. So we have to replace these values with the current ones that we have. Yeah. And then this is the private key. And then this is the setup contract address, which is the target, the target contract that we have to exploit or call the contract, the solve challenge. And then the user address. Yeah. I'm gonna save this, and then I am just going to Solve it. So it's gonna do everything for me. It's gonna connect to the RPC, the connector chain, and then yeah, it solved my it solved it's called the solve chal function from the Solidity code from the target contract that we are exploiting. And then when I go back and I click flag, as you can see, there's a flag over here. Yeah. So actually that was the only thing you had to do. Just interact with with your blockchain instance that's running, and then just call the target contract or get the target contract, and then call that exact function, and then you get your flag. But so initially I thought that niende kwa remix, and then there's a way you could go to remix.ethereum.org, and then you could connect you to a custom RPC URL. So I thought now I connect to a custom RPC URL, and then I can deploy that smart contract over here, and maybe I could get the flag, but that's too much work. So and also that means I could have to use a MetaMask for signing transaction, maybe the public key for deploying. But the problem with MetaMask is that it's stateful. So when I've interacted with other blockchains, it always stores the nonces for every instance. So that means when I'm trying to interact with it for this specific blockchain instance, itakuwa inatumia like the nonce that should be used, or the nonce that this blockchain is using. It's going to use the nonsense that I've been using with my other interactions with other blockchains. So I would always get a wrong answer every time. So that's the problem with MetaMask. It has the caching issue. So the easiest solution was to just have this simple Ethereum client, and then just and also this one was asking for the nonce from the blockchain. Don't assume that. So MetaMask assumes that, oh yeah, last week we interacted with this blockchain instance and this was the nonce, so I'm going to use this nonce. But for this script, just make sure that you ask the blockchain what's the current nonce, and then use that in now solving the challenge or attacking the target contract. And yeah, that's it. And then yeah, when you go to the page, you get a flag. That was it. So I think for a beginner, I think the first thing they would have done is just go to MetaMask, do the whole remix thing, errors everywhere. But this was the most straightforward thing. Yeah.
Is there anything to cost the solve check?
Yeah. Where did I get it?
Yeah.
I was given a code over here. This one. So I had to download this one, and then I have to pass it to the script to just tell it that this is a target contract, this is what it's expecting. Actually, it's here. Where is it? This is yeah. So as you can see, there's only one function. So you only have to call this function, and you can see child solved returns true. Yeah. You literally just have to call this software hackers challenge, and that's it. No exploit. Yeah, I actually thought it was something major than that. And yeah, but so for the flag, it was asking, is smart contract hacking really for noobs? So as you can see, a noob is a person who would have gone to MetaMask. They do the whole remix thing and everything, and that would have cost them a lot of time. And also another thing for this blockchain instance, it's for 30 minutes only. So 30 minutes the kisha ina terminate. So it's just like a Docker container. So after 30 minutes, it terminates. It does maybe Docker compose down, and that's it. So it would take you a lot of time to configure, remix, deploy, and everything. After that time yako itakuwa ishaisha. Yes, so that was what that challenge was just testing for. Yeah, this was the flag. Is smart contract hacking really for noobs? This is written in lit speakers, of course. And then the last one was a simple cryptography challenge. This was the description. A mysterious numeric message was found. Use key to read it and submit it as that. So the hint could be Russians. I think this was what gave it away. I think I'd even spend a minute on this, because you only have to when you see Russians, just search which is the most popular Russian cipher, and there was only one answer, the nihilist cipher. And once you understand how it works, just write a simple script. Or actually, I kind of overcomplicated things because there's even online tools for solving the nihilist cipher. I just thought writing a script was easier. I don't know why, but this is how it works. So we have the Polybius square, which is now, for example, so this was the ciphertext we had. We had this ciphertext over here, the 4048. So essentially what you do is just couple it together, and then you use the Polybius square and you use the keyword. So the keyword was key, the word key. So you just write key, and then you repeat it. So for K is 25, right? For E is 15, and then for Y, it's 5, 4. So what you do, you just subtract. So you subtract 48 from, where is it? You subtract 40 from the first one, which I think was 25. You do the same. So you subtract 25, 15, 54, 25, 15, 54, 25, 15, 54. And then what you're gonna get, now you look at the Polybius cipher, the square, and then see, okay, if it's 23, that means it's a J, or if it's that. I think it was so simple. Yeah. So yes, when I subtracted, I got these values, 15.325. Oh, no, this is for the word hello. But no, so this is what I was saying. So you have to, this is the keyword, you repeat it, and then you get these values, and then you subtract them. So 25 minus 48, you get a value, and then you get a ciphertext. Yeah, and then now you look at the Polybius square and see, so if it's 23, what does 23 stand for? You get maybe E or that. So that was the exact way to do it. It was very simple. So I just wrote this simple script for giving me the values. And then when you look at 15, 15 gives you E, 33 gives you N, 24 gives you J. Yeah. Yeah, so that's it actually. And then there was a cryptography challenge that I didn't get to do because personally I do feel like it was lacking context. But yeah, someone else said that it was a skill issue, which I do actually agree. Yeah, but yeah, if you know how to solve this, maybe you could give it a try. Yeah. And I think that's it for the walkthrough. I don't know if anyone else, if you have a question, a comment. Yeah. If rabbit hole was a person, that would be me. Yeah. So yeah, I don't know if you have if anyone has a question, a comment. But yeah, guys, I think we should do more of these things as much as they're not hard, they're just for fun. They teach you so much stuff. I didn't mean Ilisoma, I learned a lot from just doing this challenge. I didn't know about opcodes and everything, but right now, even you guys know as well, and everyone who's read the article. So yeah, just let's be doing this fun stuff. If you're up to do more challenges with me, more CTS with me, yeah, just hit me up. And oh, actually, Craig is here. Craig was the author of the first and second challenge, and I think we just have to, upload him for that. That was really nice, Craig. Yeah, they're clapping for you. Let me see if there are any comments. Yeah. Yes, yeah. So I think that's it for me. Thank you guys for coming. I hope you learned something, and also just go give this article a try. You'll learn a lot from it. So thank you. Uh, bye bye everyone. I think we can leave, right? Yeah, you can leave. Thank you guys for coming.